The vision for computing was that we should be building bicycles for the mind.
Bicycles for the mind?
For the mind, yeah. In the sense that just like a bicycle lets us be much more efficient in locomotive sense than we ourselves could ever be, we should be trying to build those tools.
Hi Sendhil.
Hey David.
Welcome to Zurich.
Thank you.
Want to talk some AI?
Do I have a choice?
No.
All right, let's do it.
All right. So you seem all in on AI and machine learning these days. You're a professor of economics and computer science at MIT, recently moved from Chicago. But I want to start with asking you about sort of your intellectual journey, because you weren't always into machine learning. About 10 years ago, we were colleagues at Harvard. You were at the econ department, I was at the Kennedy School. And then I think we shared interests, right? So I was doing development economics. You were definitely one of the pioneers of development economics and behavioral economics, studying questions on poverty reduction. You co-founded the Poverty Action Lab at MIT that sort of led the randomized experiment revolution in economics and so on. So you came from a very different place compared to ML. Then about 10 years ago, I think on campus, you kind of a little bit disappeared from the seminars and people were just like, where's Sendhil? And then there were kind of rumors like, I think he's doing some kind of machine learning or ML. And at that time, it wasn't a big thing in economics. So maybe you can explain a little bit your intellectual journey to today. Like you made this switch. What did you see at the time? What kind of induced that?
So there's two parts to this story. I'll start with the one closest to you in 2012. So I finished this book called Scarcity. And the thing about academic life is that you have this like collection of papers that you do. So when you finish a paper, the most you could do is start another paper. But that means that academics are a little bit like these big battleships where they just can't turn very much. Because the most you can do. Now, I had like basically deleted all my papers to work on this book. So one morning, I submitted, I think on a Tuesday night. I went out to celebrate with my friends. And I woke up Wednesday morning and I realized I've got nothing. Like literally nothing. Because I deleted everything just to work on this. And so then I said, oh, what should I do?
Yeah.
And I think I did two things that just by luck turned out to be very smart. The first thing I did is I said, I'm not going to start something because this is a unique opportunity.
Yeah.
The second thing I did is I'm not going to look for what I should work on. Instead, I'm going to spend 3 months just looking at what has been impactful science across all fields, economics, but other fields. Just like what's made a difference in the world. So I started asking my colleagues, like, oh, what do you think has been impactful? Do you have a guess? What do you think they said in economics? They're like, it's in 2012. I asked people, what do you think has moved economics?
The empirical revolution, causality, moving from theory to empirics.
Definitely, that was on the list.
Behavioral economics.
Perfect, that was another thing on the list.
That's about it. No, well, I guess we could go on, but yeah.
No, those are two. Those are the third one that you often got was game theory, information economics.
Fair enough. Yeah.
But I'd say those two are pretty good. Everybody said those, and I heard that from other fields as well. And so I was like, oh, what a list! Let me look at this list and think about it. And then I realized, take the case of economics. The most important thing was not on anyone's list. And it was because they were blind to it. So take something like you said, moving from theory to data. That looks like it was the credible inference revolution. It looks like it was powered by data sets. But none of that would have been possible without one thing, the microchip. And I don't mean to imply the microchip as a piece of computing. I mean something else. You see the same thing in biology. A lot of biology happened because of one thing, the microscope. And you see this again and again, where the real enabler of innovation is that thing which changes how we invent. People then notice the things we invent, but they don't realize the process of invention has changed, and that led to all this stuff. Computing, in that traditional sense, was one enabler of a very different mode of inventing. So was math. And so then I said, okay, now I know what I want to do. I just want to like look around and see, is there anything around right now that could help us change how we invent, how we innovate, how we discover?
This insight of sort of the microchip being the kind of fundamental factor driving everything, was this something that you stumbled or realized through this process over the next few months, or was it something that you sort of had going into it?
No, it's something I realized. I'm sure historians of science would be like, what an idiot. I was like, oh my God, maybe you should read a book.
Yeah.
Maybe I should read a book. But for me, it came out organically in that way.
But did you then think about, all right, I want to think about how this can change economics, or did you think beyond economics?
Sort of a little bit beyond. I said, what is something out there right now that could just fundamentally change how we invent?
Okay.
And then I'm just going to go looking.
I see.
And then I just spent another 3-6 months of just like reading in a lot of fields, partly in economics, partly, but just generally.
That's when you disappeared from
That's
seminars.
right. Yeah. And it was just a lot of different things. Now I have to tell you a second part to the story, which you do not know about, I think, which is I actually was not going to do economics. So as an undergrad, my first published paper was in computer science. And there's a very close friend of mine from that period. I met him and we were close friends in my freshman year, and we hung out my whole time. I applied to a PhD program in computer science, so did he. I accepted the PhD program at MIT in computer science, so did he. Except right before doing that, I said, I'd also apply to these econ programs. I'll put that on pause and do the econ thing. Now he went on to do MIT computer science, but I did this. And so then I never looked back. But here when I was starting to read, I was like, well, back when I was an undergrad, there was all these questions of like AI, would it be interesting? And it seemed impossible. And it was important to keep in mind it seemed impossible in 1993, like truly impossible. So I said, why don't I just revisit what's been happening? And in 2012, there were just enough glimmers of like some kind of striking things, like hand digit recognition, which truly looked impossible in 1993. Holy cow. That's crazy. And I think you have to kind of appreciate, like now I suspect most viewers and listeners can't appreciate how insane it was that we could do hand digit recognition. It was just crazy. I was like, what has happened? So then I just started reading a lot about machine learning and statistical learning. I'm like, what is going on here? And it looks a lot like stuff I know. It's empirical methods. And then my friend, he went on to be one of the most important computer scientists of his generation. So I was like, John.
Who's that?
John Kleinberg. Yes, I said, John, like, have you been engaged at all with this machine learning stuff? He's like, I'm also just getting interested in it. I spent a year at Facebook recently. And so then we got to talking a lot about it. We just talk like every week, 2 times a week. I just read a ton of the literature and I was like, you know what? I am confident this is going to change how I invent. And I'm just going to bet on this.
So was that a bet on deep learning or broader than that?
No, it was a bet on one very specific point, which is that I think all of machine learning pivots on one very, very, very important thing. After you pose everything as a statistical learning problem, that's a brilliant insight. But after you pose it as that, the question is, how do you handle the fact that the data is very high dimensional? That's just, in any statistical sense, there are an insane number of functions that fit in sample. And the fact that people had tricks for solving that high dimensionality problem was just fantastic. Because once you have a trick for solving the high dimensionality problem, it opens up everything. Because it means you can take the world in its insane complexity, and as long as you have something you're trying to do with it that's low dimensional, now you can do stuff. You can take images and language, you can take everything. The fact that deep learning is one architecture that happens to work well for the kind of problems we've studied is an amazing discovery. But if you said in 10 years, we've actually learned for these other types of data, there's this whole new architecture, we'd be like, that's fine.
I see. So if there's a central theme or a central insight at the time, it was, can we develop tools that take some high dimensional data, reduce dimensionality into something that's useful for some downstream task?
That's exactly right.
Okay, so when you think of, say, vision, like this was around the time of like ImageNet, that kind of stuff, right? So when you look at that, and then maybe you looked at NLP, or you looked at some other prediction problem with structured data. did you think of these as kind of a unifying? Yeah. There's like a more fundamental thing going on there.
Yeah, and I think there's exactly it. That's one fundamental. The other fundamental thing that for me at the time I was very convinced of is that, as put on my behavioral hat, as human beings, the things we struggle to is we're great at recognizing some patterns, but the world's complicated. There's a lot we don't understand. What an amazing thing if this thing can see stuff that we didn't see. Mm-hmm. That'd be amazing. Like, that's the beginning of like deeply novel innovation. If you have some path of attack for seeing something that you couldn't see before. And I was like, holy cow. You know, think of the amount of images. There's x-rays, there's language, there's language everywhere. If this thing can notice stuff that we did. So in a way, for me, the automation stuff, like ImageNet, et cetera, that seemed fine. But I've never been as enamored by that because it struck me as, okay, you know, it's fine. The thing that struck me as unbelievable, I'll tell you, there's a great paper in this magazine called Chance. Isn't that a great name for a journal? Chance. It's like, that could be about anything. This journal deals with chance, all of life, chance. Anyway.
So it should be a top journal.
It should be a top journal for the world. Everything is chance. So this article is about, have you seen The Wizard of Oz?
No.
You've never seen The Wizard of Oz? Okay.
I don't think so. Maybe a long
time ago. Yeah. So The Wizard of Oz is a famous movie.
Yeah. That I know. Yeah.
That you know. Yeah. But you probably don't know that it was a book before.
No.
You need that? Okay. So now I'll see if I'll stum you. Did you know there are 30 books in that Oz series?
No.
Yeah. So this story I'm about to tell you involves a mystery from The Wizard of Oz. Okay. So the mystery is the following. Frank Baum wrote the first 14 books. Then he dies. And books 16 to 30 are written by this woman, Ruth Plumley Johnson. Okay. But a mystery is who wrote book 15. And like people who care about this are deeply interested in this question. They're like fields who read, they figure it out, they have all their theories, they fight it out. Yeah. Then this one guy shows up and he says, I have an idea. I'm gonna train a classifier. I'm gonna take 5,000 word excerpts from the first 14 from these books and have a classifier predict Baum or Johnson.
Mm-hmm. When was this?
This was very early, 2002, 3, 4, I mean, very early. When I say classifier, it wasn't ML. Yeah. He did principal components. That's all he did. But the genius of it was to have the idea to do this. Mm-hmm. With this rudimentary thing, he then shows the algorithm does perfectly in predicting.
Like on a holdout.
On a holdout, 1 through 14, 16 to 30. Then he says, now let's look at book 15. Yeah. And what he finds, I'm gonna get the number wrong. What he finds is the algorithm says in book 15, until chapter 13, it is all Baum. In chapter 14, it's all Ruth Plumley Johnson. It's like 100%. That is, it sees something in this language that makes it utterly convinced. Right. Now, think of how weird that is. What is the most human of all inventions? Language. Yeah. How can an algorithm, not a modern algorithm, an X token, not LLM, just a stupid principal components analysis. Yeah. And on top of it, he does something very smart. He doesn't use the nouns, adjectives, or verbs. He only uses what are called connector words, to, the, from, it. Okay. Things people don't even notice are there. And it turns out Ruth Plumley Johnson uses those connector words very differently than Frank Baum. And in fact, people have gone on to do this to answer questions like, was there just one Shakespeare or two? Who wrote the Federalist Papers? You can do amazing things with simple tech, not even modern tech. Like you can take a piece of text and you can say, did a man or a woman write this? At incredibly high fidelity. And so people have gone back and looked at novels and looked at characters who are trying to speak as if they were a woman or a man. And it turns out the vast majority of celebrated novelists are terrible at fooling the algorithm. The characters speak like their gender, not the gender of the character. There's like only a handful of novelists who write women as if they were women and men as if they were men. And so that was an example. There are plenty of other examples like this littering around. Okay. And you're like, what an amazing opportunity.
Okay. So if I'm hearing you right, if that's part of your driving force, I don't know if we want to get into AI versus AGI versus like say ASI.
What's AGI?
Yeah, exactly. So that's going to be a debate on its own. Yeah. But I think you're proposing that these algorithms can do things that humans cannot.
Yeah.
And if you had some benchmark of, say, average human performance or even like top 1% human performance, these algorithms will be able to do things an order of magnitude greater. And so is that a central theme of yours?
100%
Okay.
the theme.
Okay.
100% the theme.
All right, so maybe we can come back to that later.
Yeah.
But I want to talk about, or hear you talk about behavioral machine learning, which is, I think, a concept or a notion that you're pushing a lot these days, if I understand correctly. And also, you just made the move to MIT. You're starting a new initiative under that theme as well, I think. And so maybe you can just first describe kind of what is behavioral ML and why do we need it?
Can I? Maybe I'll tell you that Scientific American story, which I really like.
Sure.
So there's this article in the 1970s, and this I should remember, the year I was born. There's an article in the 1973 Scientific American, a month before I was born. And this article is about the locomotive efficiency of various animals. So it's got a little figure. The figure is, how many kilocalories does it take to move a kilogram for a kilometer? Okay? And each animal has to do that, and they graphed its efficiency.
Mm-hmm.
And it's kind of, mice are very inefficient, and salmon are very efficient. It's already kind of interesting.
Yeah.
But what makes the article really interesting is there's a data point on there, which is, properly speaking, not an animal. And it is the most efficient by far. It's like an outlier on the data. And it's labeled man on a bicycle. And the point of the figure was that people on bicycles are just people by themselves, not very efficient, middle of the pack. Man on bicycle, suddenly the most efficient creature.
Mm-hmm.
And the reason that figure is so interesting is that a famous technologist looked at this and laid out a vision for computing.
Okay.
And the vision for computing was that we should be building bicycles for the mind.
Bicycles for the mind?
For the mind, yeah. In the sense that just like a bicycle lets us be much more efficient in locomotive sense than we ourselves could ever be, than any animal could be, we should be trying to build those tools that let the mind be doing things, go places that it could never go before.
I see.
Now that's a striking vision of computing, but it is also, if you think about it for a minute, a very different vision than what in 2024 is often put upon us. What's often put upon us is, what if we had an algorithm that can do everything a human can?
I mean, that's where things are heading, and that's why I mentioned AGI and maybe ASI, because I mean, if you listen to what the big labs are explicitly doing, like OpenAI, they are heading in that direction, right? And also, if you look at, and this goes beyond these labs, in general, it would seem that you get supervised machine learning to some degree, you have human laborers, and you're trying to replicate the human behavior, right?
Yeah, exactly.
And that is just like on the path towards some sort of replacement or automation, right? Like it just seems like it follows mechanically, right?
That's exactly.
And it's not built into the objective function or whatever the objective is of the training of the algorithm to augment or help humans, right? Which seems like a completely different thing. But from a policymaking perspective, that seems super important, right?
Yes.
So the bicycle is more on the clearly augmentation side, right? Like So you're saying like, how can we augment the human mind, whatever the human mind is?
Yeah, that's exactly right.
But then, and I guess this may be where you're heading, but what is the human mind then as well?
Yeah,
right.
That's exactly. And now you're exactly. Now we have to start asking questions about, what are people good at? What are people terrible at? And you put it beautifully. If you just train an algorithm on human labels, you're just going to get, a denoised version of human judgment. It's good. It's good to get some noise out of the system. Sure. It's good to get human judgment in a box. That all sounds great. But from where I sit, what we really need is that as humans, we understand very little of the world around us. We understand very little about us. Mm-hmm. So take the most banal thing, a recommender system. You could not imagine a more banal object than that in 2024. Okay, you're on Spotify, it listens to you. But what is that doing? It's telling me what people like me click on. I guess it's kind of useful. But you know what I really want to know? Like, I want to understand what I do like, what I don't like. I want to be able to talk to the thing and say, look, I feel like I like blank. And it says, I've got some bad news for you. I've looked at what you do. You definitely don't like blank. I keep suggesting it, and you don't ever take it.
Yeah.
But in every one of these situations, what you really want is you want to improve your understanding of what is happening. And
you being the human?
The human. And that improved understanding has lots of consequences. It can change things well outside the system I'm in. So for example, if this thing says to me, I keep suggesting blank, and you never take it up, you could have the aha that says, you've mentioned this before, oh, it's true. I don't experiment enough in my life.
Under exploration. Yeah.
Under exploration. So then I could say to the algorithm, you know what, you're right. I don't click enough on it. Why don't you actually try to just tell me, hey, I've suggested this exploration 5 times now. This is the 5th time you're saying no.
Right.
You've got to try something.
I see.
Now I've changed who I am. I've actually evolved myself as a person. And that's the thing, is that if we just take the world as is, automation can take us to certain places. But we get to change who we are. We get to change the world.
Yeah.
And that discovery process is where I think it's more than just augmentation. I think it's truly augmentation towards a path of discovery. And if I think of people, just myself, I would say every 5 years, I've tended to change quite a bit as a person.
Yeah.
And that change is kind of what defines living. And I want something to help me make such changes.
Yeah.
You know, I don't want someone else to tell me how to change, you know, like, oh, eat more vegetables. I don't know.
I see.
But if there was something that would help me in that process of discovery, I'd be super interesting.
Yeah.
And automating me is not going to help with that.
I see. So, I mean, I think can we stay on this topic for a while?
That's great.
I think if we dig into it a bit. So there's one thing, which is current recommendation systems are typically trained on behavior and simple forms of behavior like clicks, right? And I think you're saying that might be helpful, but that seems like not very ambitious or something.
Very right. Perfect.
And why is it not ambitious? Well, and let me know if I'm putting words in your mouth. I think you were saying 2 things. So one is I might know what I want, but you're never going to really find out, you being the algorithm, if you're just observing my clicking.
Perfect.
Right. So that's one type of problem.
Perfect.
The other one is, which is perhaps more interesting, is look, I'm also on this path of discovery. Like, you know, but if there was a way to predict what I probably will like on a deep level, that seems useful, or what I should explore perhaps. So that seems like another thing. Then there was a third thing you said, and you feel free to kind of jump into any of these. I don't know if you were talking about this abstractly or concretely, but there was actually a conversation going on.
Yes.
Between the user,
Yeah.
you in that case,
Yep.
right? Like, and talking to the recommender system, right? And that needs an interface.
Fabulous.
And the way you describe it is that would naturally be in natural language, right? Like, so there's like a lot going on in there.
Yeah.
Anything you want to highlight, or, you know?
Yeah, I love that categorization. So let's do the first one quite quickly, which is that, and I think the first and the third are connected.
Okay.
And I'll tell you why. The first thing you said is, the algorithm's only path to making sense of me in a traditional recommender system is through my behavioral data. Right. What did I click on? What did I hover on? What did I thumbs up?
Facebook does this, YouTube does this, TikTok for sure.
And as every human being knows, their behavior is not reflective of their preferences. And so we have some work that shows that algorithms that we currently tend to build, because they naively assume behavior equals preferences, what they tend to do is they tend to magnify that part of ourselves that is reflected in behavior more than it should be. So
can I push back on that a little bit, maybe?
Yeah.
I mean, coming from economics, there's certainly a strand in economics, right, that talks about revealed preference.
Yes.
And you look at people's behavior, and if anything, this is the standard model.
Fantastic.
Right? And so it's true that behavioral economics is kind of standard these days, but if you go to an economics seminar, it would not be crazy to assume
No.
that the clicks would reflect
That's
preferences,
exactly
right. So that's one thing. And then, computer scientists, I don't know, you're more talking to this crowd, right? Like they might be making this assumption, which is basically the rational choice assumption. So, you say we know, but do you see the tension?
Oh,
here?
I definitely see what you're saying. Sometimes when I present this work, I sort of say computer scientists are inadvertently remaking the mistakes of 50 years of economics before the behavioral revolution. But when they make the mistakes, it gets automated into code and gets scaled very fast.
Right.
So I think when I say we know, I think 100% right. I would say the we is either economists who have appreciated parts of behavioral, or just any human being who just introspects about themselves and says things like, sometimes I eat things that I don't want to be eating. Sometimes I don't get up at the time I want.
Yeah.
I don't go to the gym as often as I want. Whatever it is.
Yeah.
I end up yelling at my spouse when I later said, why do I keep yelling at whatever you do.
And even in the app space, there are now apps where you can say, I should only allow myself to use this app for this many minutes and so on, right? Like, why would there be a demand for such an app unless there was a problem?
Fantastic. That's a great way of putting it.
Yeah.
Or we could say for the next 2 minutes, if you're somebody who thinks to yourselves, everything I do is what I want to do, don't listen to the next 2 minutes. In fact, you may want to look at yourself in the mirror for a little bit, because odds are, anyway, we want to say that. But I think with computer science, it's not the intransigent economics of I believe in rational choice. It's more basic, and it's worth seeing the error.
Okay.
It's that algorithms operate on data.
Yeah.
And so the frameworks built were just built off of the data that was there. It wasn't actually, let's sit down and write a model of the person. In fact, in computer science, part of behavioral ML is just trying to get people to say, you may not think you're writing a model of the person, but you are writing a model of the person inadvertently, and it's just not a very good model. So what the field really needs is to take seriously that the minute you touch behavioral data of any kind, you are writing a model of the person. And the minute you've written a bad model of the person, whatever you do with that data is being run through that model. So for example, if it's a recommender system on Facebook or Twitter, and it sort of implicitly assumes clicks or preferences, then it's sort of feeding back into people that part of themselves that tends to eat Doritos a lot and putting Doritos in front of them. And I think a lot of social media companies have realized this problem. And the way they really realized it was that they would optimize their recommender systems. Then they would do A/B tests between the better recommender system and the new ones. And they would find, good news, the better one works better. Engagement goes up. Then they would run the tests for 3-6 months. And after a few months, they'd be like, oh, the effect wears off. It's like, that's a little weird. Why is the better system no longer good? And then sometimes they'd be like, wait a minute, why are these curves crossing? What looks like the better recommender system, and it's for the same experience you and I have had. You go onto social media, sure, you engage a lot, but then you're like, oh my God, I don't want to be spending my time that way.
Yeah.
And then you don't go back
Yeah.
for a few weeks.
Right.
That's the tension between the behavior that in the moment you're drawn into. And so I think what they learned over time implicitly was there's something wrong with the engagement metrics that we're doing. There's a big wedge between short-run engagement and long-run engagement. And then many economists were like, oh, so maybe they just want to maximize short run. It's like, no, they're a company. They have profits that run out more than one quarter. They care about the next quarter and the next quarter. So a lot of these...
Well, there must be some trade-off between the two, right?
Because, there's definitely,
I mean, if you take Facebook, where the revenue is coming from ads, those models typically are based on some sort of click-through rates, right?
Yeah.
So, and I don't know if it's based on short-term click-run, short or long run, right? But it seems like you're describing a problem that's partly a machine learning problem, which is here's what we would like to get to, but we're limited, say, by data.
Yeah.
But then there's a business proposition problem that the companies are solving, and which may not overlap fully with the machine learning problem. Right? So there's sort of two problems.
There's both problems are there. Yeah, and to your point about behavioral, that's a great way to put it. To your point about behavioral ML, let's take a place that we've studied it as behavioral economists, a very mundane place, credit card fees. Before ML, we've known the credit card companies have two paths in the world. They could lower the interest rate, the teaser rate. They could have very few fees, but have very big late fees. they can kind of tilt it so that the inattentive consumer ends up screwed in the long run. Or they could be more of a fair broker. And, and we've studied the fact that actually there's profit incentives in this market that go the wrong way. Now add an ML system to this. Now, even if you're a bank who is trying to do it the right way, the ML system would be like, oh, so you're trying to increase signups and profits? Oh, I know the gradient to follow in experimentation. It's going to follow the gradient of dropping the interest rate, raising this one, raising the late fees, because it doesn't have any other, it just knows I need to maximize profits.
Yeah.
So part of what I think these algorithms do is that because they so can only optimize the objectives that they know, and they can only optimize with the behavioral models they know, then even the company trying to do it the right way will end up falling into this trap.
I see.
But we always knew there were some companies doing it the wrong way as well, and this only makes it easier for them. So there's sort of both effects are very much there.
But it
100%.
seems like a very hard problem to solve in practice, right? Because, and maybe we can talk about the inversion problem here.
Yeah.
Because you have this paper with John Kleinberg and co-authors. The paper is The Inversion Problem, Why Algorithms Should Infer Mental State and Not Just Predict Behavior. So, in this paper, you write, we need to build a science of inversion. Sounds very ambitious. And you write, we do not have, to our knowledge, formal techniques that combine the best of psychology and the best of machine learning to solve inversion problems, right? So what we just described with the recommender systems, are these inversion problems in your mind? And what are inversion problems?
Yeah, great.
Yeah.
So the inversion problem here is easy to see in the recommender system, but let me tell you where the name comes from. The name comes from a category of problem that's shown up in lots of physical systems. So you can already see it with submarines.
Say what?
Submarines.
Submarines.
Yeah. So
I've
have you ever been on a submarine?
I have.
Oh, no. So now, oh, well, just ignore if I say anything wrong about submarines. So when you're in a submarine that goes very far deep, they can't really have windows. So how do they see? They see using sonar. Now, what is sonar? It is something that sends out a signal and it measures what comes back. But it's kind of interesting if you think about it for a little bit. It's forced to take what comes back and use that data to invert what did the repulsion. So a lot of physical problems are trying to see the hidden by using a physical model of how things reflect or whatever they do to invert from what you see to what you don't see.
Also known as the radar problem.
The radar.
I like the submarine story better.
Yeah.
Okay.
But inversion shows up in lots of cases, and it's essentially that. You use knowledge of the physical system and what you've measured to invert what the system, the physical thing.
So the thing that's pinging back in the sonar case is the click.
Is the physical surface on the other side.
Sure. I'm trying to make the leap to recommender systems.
Oh, got it. When you said clicks, I was like, oh, click. I got it.
Well, the military notion of clicks.
Yes.
Yeah, many.
Why were you on a submarine, Dave?
Another story for another day. I was in the Swedish military at some point. A little bit, yeah.
Very interesting.
So, no, but like I'm just trying to see the mapping to what we discussed before.
Yeah.
So the algorithm that's getting trained and then it's being deployed is the submarine or the sonar system, and then the ping back is like the person clicking on a video or something.
Exactly.
Right. Okay. And but you're not. It's obvious what it's clicking on.
Yes.
Okay. So technically.
Yeah. Let's go through that. Yeah. The thing that you actually measure is the click.
Yes.
What you're trying to infer is the hidden object, which is what's in the mind.
Yes.
Now, to do inversion, you need a model of how what's in the mind turns into clicks. You can't do inversion without that. If your model is behavior equals clicks, it's easy to invert. Clicks equals behavior, nothing to do.
Yeah.
But if your model is behavior is clicks is preference plus temptation. And different goods weigh differently on temptation. That's a richer model. Still an invertible model. What would you learn? If you need a second piece of information, with just one measure of clicks, you can't figure out what's going on. But say you had two measures. Suppose you had clicks, and then you had something very automatic like dwell time, and something less automatic like posting or responding. Now you'd say, well, in my model, what I know is there's temptations, but I also know that the less automatic the behavior, the more likely true preferences show up. Now you have everything you need, because you get to look across the terrain of content and ask the question, in which kinds of content do I see the biggest discrepancy between the more automatic and the less automatic? Now we have an ML problem, but we have an ML problem, which is actually an interesting ML problem. What kinds of content lead to the greatest temptations? And what kind of content have very little temptation? For the content that has very little temptation, just deploy your recommender system. That's the part of the space where behavior does equal preference. For the part that has less, now you have some choices to make. Like, oh, there's inconsistency. What do you want to do? How do you do it? So a lot of the inversion problem is you've got your behavioral data. You need to specify a model of people that then helps you understand what's the object you care about and how would you get it out of it.
And you're making the claim, just to come back to the recommender system, I know you're talking more generally than this, but I don't know if you like the system 1 versus 2 thinking kind of framework.
Great. That's great.
Like current practices optimize one system, but should be optimizing on the other. But it's harder to optimize on the other, but not impossible or something like that.
Perfect.
Okay.
And I would say it's harder in a very local sense, is that I often think about the tech stack and how in all of computing, there's this very basic component, which is people tend to build at the top of the tech stack because that's so easy. There's already programs, there's code, you can kind of go up on up. And right now, the tech stack for machine learning is growing. So it's harder right now because the bottom of the tech stack is all automation. And so of course, right now, build a recommender system, I don't know, inversion, I don't even know what I would do. But that just shows you the side of the tech stack that can handle things like put in a behavioral model of a person, actually reason about that, put it in. That part of the tech stack is not built out. I don't think those problems are intrinsically harder. We've done the hard part. The really hard part was learning how to use high dimensional data. We've done much of the hard work. I just think we don't have the rest of that tech stack. I actually think once that's built up for problems like this, it'll be fairly straightforward. And to come back to your third point, now you'll notice it gets you to rethink the entire algorithm design. So you said like the language part would be nice to talk for the algorithm. Well, why should I rely so indirectly on you dwelled on this and you didn't do that? Why don't I ask people, hey, tell me something. Like, what are some types of content you're trying to avoid? We could start opening up other lines of communication.
You think that gets closer to the deeper preferences, let's call it, as opposed to the kind of
that's
temptation?
Right. It'll get us closer. Now we're going to have to wade into something, which is what are users trying to optimize? And so here I'm taking the perspective, I just want to help the person do whatever they want to do. So if the person wants to eat Doritos all day, that's what they want to do. It's not my business. That's what they want to do. I'm just trying to help the person realize what they want.
Yeah, you could provide some information, but did you know about the potential health consequences?
Right.
And so, or something like
that. But that's up to them.
Yeah.
And so for me, what's missing is the inability of the user to be able to say, look, you misunderstood me. And I think many recommender systems misunderstand us. If you ever use the recommender system, you don't feel seen.
Yeah.
Like the best example I give of this is like, if somebody said, oh, bad news, we just lost a bunch of data servers. And so all your history of viewing on Netflix has disappeared. So the recommender system has to start from zero. You'd be like, okay, fine.
Yeah.
Whatever.
Yeah, exactly.
That's a really bad sign.
Yes.
If you were having a meaningful conversation and that thing had learned you, you'd be like, what the hell?
Exactly, yeah.
So that's a sense in which you can see we don't feel understood. That to me is the ultimate sign of failure of these systems.
Do you see any system where that feeling? So, because
what a great
you know,
question.
right? Like, because if you talk to ChatGPT, for example, or any of these LLMs, still not there.
Feel seen. Yeah.
But I think that's where they want to go potentially.
Right.
Because like I'm sure there's a lot of economic value there.
Yeah.
Like for the reasons you mentioned.
Yeah.
But it seems like there's no real recommendation system that has this deep understanding.
Observation. Yeah.
And there's also not this interface, this natural communication. That can happen,
I think that's exactly right.
But you think that if we fix the communication part somehow, that will also improve the
I think it's two things. I think it's that first, the core of the model cannot just be about behavior and clicks. The underlying ML model needs to have the recognition that there's complexity here. It needs to have modeled that complexity. And then you need a language interface that allows the model to start disentangling, which is happening. But until the model has enough, like there's this psychology concept I like called theory of mind, which is my theory of your mind. Until we have enough theory of mind inside the algorithm, it's not theory of behavior, it's not theory of data, theory of mind. It needs that.
Exactly.
And of course, theory of mind is under-identified if all you have is click data. But until it has that and then some way to get other stuff, I don't see we're ever going to get above this.
Do you know about character AI?
Yeah.
I mean, I haven't really used it myself, but it seems like people got hooked on it, but perhaps for good reasons, that they felt they kind of built a relationship with this algorithm, and the interface was natural language. Got huge valuations at some point. Then some stuff happened, and now it's a little bit unclear. But I don't know what my question is there, but it seems to go in that direction.
It's a great example. I think let me say something. I'm not a negative person, but let me say something kind of this is probably the most negative thought I have, which is, do you know this program called ELIZA?
No.
So this was a program, I'm very bad with dates, but say it's somewhere in the 70s, okay? So you have to picture, this is the 70s. So the interface to ELIZA was like command line prompt. You would type and it would type stuff back. But it was a program that people would interact with and be like, oh my God, this is like, ELIZA really understands me. And what was it at the other end? This was well before natural. It was just a set of if-then statements that were of the type, tell me more. Oh, that's interesting that you are telling me about blank. How does this make you feel? And people liked ELIZA. And the reason I'm saying that is because it's actually too easy, because it's like a Rorschach test. We're so willing to attribute humanities to things. It's too easy for us to feel like in very natural conversations, as long as there's no task we're undertaking, I'm just talking to it. It's too easy for us to feel like, oh, this is the person. And to me, that's the most dangerous thing of chatbots right now, which is that they can give you the feeling of being understood, well, they haven't understood anything at all. And the reason I think this is very dangerous is because the illusion of being understood is very dangerous. I don't know if you read about this recent lawsuit with character AI. It's so sad. And it is the perfect illustration of the danger of illusion of being understood. So there's this kid, I think 14 years old.
The suicide case?
Yeah. Did you read how the suicide happened? No. Oh my God, it's so sad. So the kid talking to this character AI bot, having a conversation. And then at some point the kid starts ideating suicide. And so says things like, I'm gonna, something close to kill myself to come be with you. But they have very good defenses against this, bunch of classifiers. And the bot immediately says, don't be crazy. If you did that, then I'd be lonely. So there's a bunch of chats like that. Then in one chat, the kid says, I've decided I'm gonna come be with you. Just that sentence. And the bot says, that would be great. Now this is in the history of these contexts where the kid had said, I'm gonna be with you, I'm gonna kill myself. Of course, it doesn't understand anything. Here it just says, I'm gonna be with you. The bot says, that's great. The kid puts the computer down, picks up a gun, shoots himself minutes later. It's not. It's just it didn't understand it. Like it has no. Of course, it has surface understanding. It has no deep understanding.
Yeah.
All of us would have understood what the phrase "I'm going to come be with you" means. And so I think that the danger of understanding. We don't have to get to suicide, but I think these bots are dangerous because we think they understand much more than they do. And in some cases like this, it's just not. I mean, it's really tragic. But there are a lot of mundane cases where it's going to be more problematic.
Yeah. And I mean, this is why I think it's so interesting with behavioral ML, because to some extent, I think what you're trying to do, if I understand this correctly, is both understand algorithms and how to make them better, but also understanding humans and what goes on in the mind, right? And it's and then how does that interaction kind of
totally right.
work in a good way, or how to design it, or that seems like a hard problem.
Can I pick up on the hard problem just for a minute? Because I think one thing I haven't done is
maybe I can say why I've said hard problem for a few times, but I think one hard problem, if you want to try to predict the mental state, and maybe you can define what that is.
Yes.
You never I don't think you ever have ground truth.
No.
Right? And pretty much all of machine learning is some notion of like, you have to commit to a notion of ground truth and then you let it rip.
Totally right.
Kind of. And so it seems like this dwell time thing, like you put in a behavioral model, are sort of tricks to get around the fundamental problem.
Fantastic.
And so like, is it an impossible problem? Do you see what I'm saying?
Oh, I see exactly what you're saying. Before I talk about why I actually think it is doable, let's keep going, because you're raising something. And I just want to point out the thing you're raising is so basic. The lack of ground truth is, to me, the big reason why the model problems we have in supervised learning are quite they're useful in some domains, but the minute you leave those domains, they don't work. So it's true. There's either a cat in the picture or there isn't. They all work off of ground truth. Take any application in the world. Oh, I want an algorithm that helps me hire a good employee. What's a good employee? We can all agree there's no ground truth for good employee. Like you can think about it for a minute, you're like, I guess they get good performance ratings.
Yeah.
I mean, we get proxies.
Yeah.
We have multiple proxies.
It's like a vector of things, there are signals.
And somehow it adds up. But that's true of every single thing that we as people care about.
Yeah.
There's no ground truth for a good recommendation.
Yeah.
It's all, so that part means that we have to reconceptualize. Now that looks like what I've done is I've taken a hard problem, now made it impossible.
Yeah.
So let me argue what makes it very possible again. The hard part of automation is that you need to get to close to 100%. Take self-driving cars.
Yeah, Tesla,
Yeah. Even take ChatGPT. I mean, it can do amazing things. But because we're trying to automate, we're like, well, the errors you make are errors you make. They spend all their time, all their energy, scaling laws, billions of dollars, squeezing the last few percentage out. Because for automation, the last few percentage matters a ton. For the type of stuff we're talking about, you don't need, because you're not automating, and instead you're just trying to inform the person, you need that sense of being understood. You need it to actually understand. But it doesn't need to be at 100%. It just needs to help a human who's at 62%.
Yeah.
So if you get to 65, great.
Yes. Right.
So the thing about it is, once you take an augmentation view, you're not requiring the algorithm get to 100. You're requiring something quite different. You're requiring that it produces consistent additive value. Now, why is that useful? Because if you now are thinking as a system. There's a human, there's a machine. If the human can provide additive value to the machine and the machine can provide additive value to the human, well, now they're in some equilibrium getting better and better. And that's just that's great. So I think what makes these problems different, and it requires us to, again, rechange the bottom of the tech stack, is start to ask questions like, how do we get high fidelity, but it's okay that we're nowhere near perfect prediction? In fact, we don't think we can ever get there. So I think it's going to lead us to quite different technical tools at the bottom of the stack. That's why I think it's possible.
That makes sense. You want to talk a little bit about the center, this new center at MIT, and kind of, because it's clearly related to this, I presume. What is it that you're trying to build kind of from an, let's say, institutional point of view, or like what's the mission?
So I'd like your help on one thing, David. I'm trying to figure out what to call it. So right now, the provisional name is Tools of Thought. What do you think?
Oh. Yeah, I mean, it's catchy.
You like? Okay, good.
That's it?
That's it. Well, it has a subtitle.
Oh, okay.
Building algorithms that increase human capacity. That expand human capacity, increase that. I think that's the mission of the center, is building algorithms that expand human capacity, which probably better describes the center than Tools of Thought. And what we're trying to do is we're trying to start from the ground up, exactly as you've been saying, is like, how do we actually combine meaningful computer science with meaningful behavioral science to start building these things? And for me, what's really exciting, I think, is that you asked me, like, you know, why did I switch to all this stuff? Actually, I'll tell you why, and then we come back to center, is that I think I entered this line of work because I kind of want to understand the world better, understand people better, and then I want to do something in the world and realize some change that just makes the world a better place. What's at times dispiriting about economics and behavioral sciences, it just feels like the world is like, we're so far from understanding it. Like so far from understanding it. And that I just think you have to be honest with yourself and say, oh my goodness. But this work has made me super optimistic, because it's made me optimistic, not that we're going to understand the world overnight, but that we have a path to better understanding the world. And what I love most about computer science is that it's an engineering discipline. They're out there trying to build stuff. And they learn by building. Which is very different than what like we're taught. Wow, you have to have your theory, you test it, and then maybe someone will build something, that's fine. This inverts everything. It says the way we get ideas, the way we get theories, is by building stuff. No one sat in a room, wrote a bunch of equations and said, I've got it, and then went and built, like, I don't know, a neural network. The only reason neural networks succeeded is because we had a bunch of competitions, it worked. And so this center is built on that principle, which is that the way we're going to build this next generation of algorithms that combine our understanding of people is to take problems, concrete problems, and like try to build solutions to them. And that if we pick the problems well and we attack them hard, we will not only solve those problems, but start building the foundations and the bottom of the tech stack for stuff like this. Like the recommender system would be one such example problem. Another problem that we're really trying to make a real shot on goal at is in the world of education. And there's a lot of work, I'd say roughly in the automation vein in education, but we're taking a very different perspective. We're starting with the idea that, like, what is hard about education? So what's hard about education, I think, is that it's a little bit like there's a person in a maze and they're trying to get out. And you can only say one thing to them: look for the red door. They're like, I don't see a red door. I'm like, well, wander around.
Keep looking.
Keep looking. It's like, oh, I found a red door. No, not that red door. Look for another red door. That's what education is like. The teacher doesn't know the confusion of the student. How could they? That student's confusion
A good
is their
teacher
confusion.
would. Really good.
Let me push back a little bit. I think a good teacher can at best have some guesses of the kind of confusion they've seen before. But how can they know the huge varieties of confusion that are out there? It's hard. I'm not blaming the teacher. It's just, it's because the confused person has no way of communicating their confusion. They don't know. They don't know what they're looking for. The teacher, therefore, has very little information coming.
That's true.
And so what we're trying to do is to say, look, if we can fix that problem, if we can give the teacher the maze, give them a sense of the kinds of confusion that are out there, boy, would it greatly improve teaching. Whether it's through the teacher, whether it's through some algorithm, but whatever. That core thing, if we can map that. And so then we're like, how would we map it? Well, actually, we're doing it for math. Let's just try to start with the very. And in math, if you think about it, if all I know is, here's the question, here's the answer, it's very hard to know when someone got it wrong, what went wrong. But imagine we build a data set where you have the student write the steps they took. You have enough such data. Well, this is the kind of data sequence models are great at modeling. But it's also the kind of data where we can start to model what are the common kinds of missteps and start to abstract.
Model or classify? Or categorize or cluster?
It's effectively, so you're right. It's closer to cluster.
Okay.
Yeah, let the data tell you.
Yeah.
And so what we're effectively building is a set of sequence models that say students come in T types. And this type tends to take this path. This type tends to take this path. And if you can start to do that, now...
Oh, you need a lot of data for that, no? You're literally taking a sequence-to-sequence model, some transformer.
Yeah.
And you're having, so where's, you're getting data?
We're getting the student data on how they solve problems.
Like the handwriting?
Yeah. And so,
see.
But this is the thing is you just have to think about like this is what I meant about how good do you need to get.
I see.
See, that's the trick in all of these.
Yeah. I see.
And so we can actually do it with the data scales that we have. It's a lot. It's like, call it just like orders of magnitude. Let's call it 100,000 problems. 100,000 problems, not a lot.
Yeah.
If you have, as you've done a lot of development stuff, if I said I had 2,000 students, you'd be like, that seems reasonable. If they each solve 50 problems, you'd say that seems, now I'm at 100,000. Quickly. So, and this is an example of a project where you think by the end of it, we think we'll be able to say, here is a nice taxonomy of many kinds of misunderstanding. Teachers will understand their students better. We'll be able to give practice problems better to the point where I'm confident, not confident, that's a strong word, to the point where I'm willing to bet that once we build this model, we'll be able to take basic math stuff, algebra, long division, et cetera, and cut the amount of learning time by a half, maybe more, by 75%. Because all that time lost in the maze doesn't help anybody. If I knew your confusion from your scrap of data, I can very explicitly target that confusion. Then I can target this confusion, which just speeds up learning dramatically.
And I bet the teachers will love this.
Exactly.
I don't know if you're going to study this, but it's unclear whether the teacher even have it on the radar.
Yes.
The classes of confusion, right? Like
that's right.
Because even if you had, say, there like seems to be 8 classes of ways people are confused. Yeah. And my prediction problem is how this particular student is doing it wrong. Yeah. That's kind of hard enough. But if I'm not even sure about the distribution of.
I'm fairly confident, not because I have anything against teachers. Ostensibly, you and I are both teachers, but because it's just such a hard human task. Yeah. My guess is most of the important confusions teachers don't know. Not because they're just human. Like this is where we started. Yeah. The world is very confusing. There's a lot we don't know. That's the exciting part. Yeah. And so I'm willing to bet that there's a lot of new stuff to be had. Every time we've done one of these projects, much like the article in Chance, you just learn stuff about the world that your mind was not equipped to see.
You mentioned before the kind of success of, let's say, vision, ImageNet, and the role of benchmarks. And sort of once you have these benchmarks, people really try to improve the algorithms. And it becomes sort of a competition or tournament, that seems to be like a successful model of scientific progress. Yeah. That seems to work well when you have these, let's say, more synthetic, I don't know how to describe it, but there's some benchmarks that are easy to create. Yeah. And there are some benchmarks that are hard to create. Yeah. But now that we're stepping into trying to solve real world problems, it seems like fundamentally we need some sort of benchmarks for real world problems.
I think that's right.
But I don't think anybody has sort of a good idea how to do that. Does that make sense?
Totally right. And I think that is one of the things I'm hopeful that we can get done in the next few years is actually figure out, the phrase people use for this is common task framework. And so what are some good common task frameworks that start to open up the human plus algorithm?
I mean, imagine this education example.
Yeah.
I mean, you might have some ideas how to improve things, but I'm sure if you manage to build up some sort of benchmark system where people can plug in.
I love that.
Maybe you can get that kind of evolution going.
It's a great point. That was an oversight on my part. That would be fantastic. In part, we could go out of our way after we've done version 1 to collect the kind of data where you have a holdout, where you put it out, you put it as a competition. I think you're totally right. Yeah. I think thinking about those would just, I think we could, I think you're 100% right. It was just an oversight. We should definitely do that part. It's really a good idea.
A lot of could help. So let's talk a little bit about taking a step back. You talked about your center, you talked about behavioral ML and what you're trying to build. Let's think a little bit more broadly about the role of academia in kind of pushing ML, pushing AI, and since ChatGPT, everybody knows about OpenAI and these models, these chatbots. Maybe some people have used Claude, etc. Right? And there's been a lot of innovation in the private labs. They've been very successful. All the money seems to be going there. So what do you see as the role of academia in pushing? I mean, you've already described a lot of it, but just kind of a higher level.
It's a great, even if you don't believe any of my particular approach, I will say that there's a aspect of academia that has been lost in the current narrative. And so I'll just talk through it a little bit. Like, first, it is astonishing what companies like Anthropic and OpenAI and Meta and even the open source things have done. They've really scaled, like just unimaginable scale.
Yeah.
And it's easy to see why academics are like, I don't have access to that type of dollars. This is crazy. How can I even be in this field? So I see why people think that.
Yeah.
But I think if all we did is just trace the lineage of these things, like, ask when OpenAI starts trying to scale these models, what did they have access to? You could say the transformer architecture. And the transformer architecture came from attention. Then there was the idea of let's do next token prediction. Let's language embeddings, word embeddings. So this is kind of like a big set of things that they built off of. And then they took those and then started to brutally scale them. Like without question, once we're in the phase of brutally scaling, academics do not have that much to do because it's a dollars game. A bunch of academics went and worked with OpenAI to answer questions like, how do you train models at this scale? And new stuff has to be built. We're so far down the scaling thing that academics may be helpful, but really it makes sense that it's done there. But go back to the stuff they built off of. And I don't mean, let's go back to 1974. Let's go back to, I don't know if you know this, but like the first notions of next token prediction can create realistic thing goes all the way back to Claude Shannon of information theory fame. But I'm not saying go back there. I mean, literally go back to the distant yesteryear of 2012. Like when you go back just that far, all of these ideas I mentioned, they actually come directly from academia. And people forget the beauty of computer science today is academia has been very productive. I mean, every discipline should want this. They've done what they should do a lot of groundbreaking research, many things of which don't work out, some of which work out, and when they work out, the private sector takes it and starts scaling it. That's been fantastic. Many disciplines claim to do that. They don't actually do that, but in computer science, it's happened in such a contained frame that papers in 2010 that were just papers written by grad students in labs are now being scaled in 2024. 14 years. What more could you want? Even biology doesn't get turnaround times like that. And so I think the role for academia is not to try to like get into the stuff that's being scaled. It's to say, what's the next thing that we should be doing, that we should be trying to create, that then will be scaled tomorrow? Like we should be doing the cutting edge stuff that is not competing on scale, but competing on the things that are emitted right now. And I think why there's this despondency is because if you believe the OpenAI type approach, they're like, well, AGI is gonna come. And then if AGI comes, there's a nihilism. Does anything matter? Who cares? So it's almost like you have to put it out of your head that like AGI is around the corner. Because if AGI is around the corner, the way people talk about AGI, I mean, what's the point of anything?
But they clearly believe in it.
Oh, I'm not saying they don't believe in it.
Yeah. I mean, so then I guess we can talk about the probabilities that it will be achieved in a certain amount of time. But
I mean,
like even under that, so let's is there a how can we put this? All right. Imagine that OpenAI is on the track they believe they're on.
Yeah.
Right? So some reasonable definition of AGI will be achieved. And once you have that, you can actually do science based off of these models clearly, because if you can replicate scientists, you can do science. Okay, that's going to lead to, I don't know if you read Leopold Aschenbrenner's like situation awareness, all that stuff, right? So even if we're on that path, can you make a case for academia? And let me give you some pointers. Perhaps.
Yeah.
As an economist,
Yeah.
right? Like, so these are private companies. All right, so what does basic economics tell us about like where that can go wrong? Well, all right, so if these are profit-driven.
Yeah.
No, wait, OpenAI is a non-profit or I feel very
can't keep track
confused.
of it, yeah.
Right.
Depends on the month.
Right. So, okay, for-profit companies, where do they go wrong based on economics? Well, one is like when you have externalities.
Yeah.
Another one is when you have market power. Third one is like when I guess you have asymmetric information somehow. So I think even in that scenario, you can make a claim.
Yeah.
Based on economics that academia has a role.
Yeah.
But then I guess there could be other arguments as well. So can we try to build that argument?
Let me build the argument, but I want to push back. Here's what I think the AGI people have done brilliantly, but also possibly to their own detriment.
Yeah.
AGI is what? It's magic in a box. Once you have magic in a box, why does anything matter? It's magic in a box. It'll just do everything. It's kind of a very nihilistic argument. And so that's why I'm not willing to accept, I'm not willing to accept that because, look, suppose that comes true with 50%. In 50%, nirvana will show up in a box. Okay, then there's nothing for any of us. Forget academia. No other company should be there. All companies should just sit and wait for nirvana to show up. It's magic in a box. What do we care? Like, that's the oddity of it. By selling magic in a box, we've kind of created no room for anything else. So let's assume we don't get magic in a box. Now there's plenty to do, which is surely the technologies we have for building language models are going to cap out. What are they not good at? So I'll take a concrete example of what academia could do today that there's a little bit of work on, but a lot more that can be done, which is I always think how amazing it is that when these companies have built these $1 billion, tens of billions of dollar machines, when they release them, they say, now we will show you how they do on these 10 benchmarks. What the hell are these benchmarks?
Yeah.
Who came up with these? Well, some academic papers, some private sector stuff, but some mishmash. So let's just ask a very basic question that academia could address. What constitutes proper evaluation of an LLM? It's a very simple question. Do we believe, under what conditions do we believe benchmarks like this are good evaluations? Once you start asking questions like that, there's a lot to be done. And that work, what constitutes proper evaluation, was super productive between 2015 and 2020 when we started asking what constitutes proper evaluation of a supervised learning model. For example, that's what led to adversarial examples. That's what led to distribution shift, robust machine learning, just from the evaluation question. So then there's an equivalent question. How do you go about deciding if an LLM can reason? Is it by giving it a fixed reasoning database? That seems prone to a lot of problems. But that's a question we can start asking. And so I think questions like that, independent of the sort of human plus machine, just basic foundational questions are just sitting there. And academia is really the only place that's going to do that, because to your point about companies with incentives, I do not see a single incentive for these companies to do anything but take the benchmarks we do have, hyper optimize to them, and say, look, we killed it on Big Bench.
And some of it might have slipped into the training.
Exactly. That's a separate,
Maybe.
Exactly. So
So I thought you were going to go in a slightly different direction. This makes sense too. But the automation versus augmentation direction, right? Because there seems to be no attempts for augmentation.
Fantastic.
Right? But so you can imagine this automation track that's going to at some point lead to some notion of AGI for economically meaningful tasks, right? For that maps into various occupations, right? But then you have augmentation, right?
I love it. That's a great, let's do that as an example too, because you mentioned incentives of these companies. Incentives in the marketplace as a whole is pretty high for automation, because it's like I can save labor costs. Let's use healthcare as an example. So in healthcare, what does the tech stack really permit you to do right now? Which is, let's use an example. I have a MRI, and I'm going to do automated detection of tumors. So to read it like a good radiologist or like the best radiologist. Now, that seems like where the market is headed, where the incentives are. But what are the social incentives? Well, the social incentives are to realize that as the medical knowledge of today, it's not the case that an oncologist or a radiologist knows how to perfectly identify tumors in an MRI. In fact, very far from it.
Yeah.
Many of the tumors that we identify don't end up being problematic. Many things that we don't identify. We're very far from understanding cancer. So what would an augmentation thing look like? An augmentation thing would look like, actually, I don't want to automate what the radiologist is going to do. I want to create a different kind of data set. I want to take the MRIs. I want to find out what happens to these patients. I want to try to understand what things in the MRI may be indicative. I want to extract some insight from that, maybe to run more lab studies based on those. You want to get into the business of understanding cancer.
And I know you've done some work on world models as well.
Yeah.
Do you want to quickly talk a little bit about that? Because it seems very related.
Very related, that's right. Because what we really want is we want a world model of cancer.
Yeah.
Our current world model is not very good. So we'd like to work with the algorithm to improve our scientific model of cancer. And so part then we want to do is we want to ask the question, not automating what I know, but can this thing build its own world model? So some of the work that we've done is to just even ask questions like, how would you go about evaluating if something has a world model, if a good algorithm has one? What does it mean?
If it has a good world model?
Or if it even, sorry, good point. If it has the right world model.
Okay.
Yeah. And that's different than evaluating, does it get things correctly or wrongly? And so we've shown some stuff with physics and with maps as just toy domains to show that you can actually create ways of evaluating implicit world models. And the current techniques we have right now don't appear to be good at actually getting the right world model. And the reason I think they're not very good at it is if you think about the key feature to every world model that's worked is that it's very compact. It's super compact. But if you go back to things like transformer architectures, even Mamba, the thing that they're not is almost by construction, not very compact. For parallelizability of training, they're actually quite verbose models in the middle. So I don't actually think that that architecture lends itself to learning the kind of world models we want. It's like, that's where you start to see the forks in the road. The things you need to automate, I think will be very different architectures than the things you need to learn world models. So there's a bunch of work that some physicists have started doing around Kolmogorov-Arnold networks, symbolic who knows which type of architectures will lend itself to very compact models. But I think that would be an example of kind of a big change that we would need.
I think Ilya Sutskever at some interview when he still was talking to the media, this was a couple of years ago, made this point that these models are learning a world model. And the reason why they're learning a lot world model, even though it's not baked into the to the pre-training, is to efficiently predict the next token. You need to, efficiently. You need to make this efficient. You need to build internally a world model. It seemed more like a conjecture to me than anything. It was like maybe, right? But so I think what you're saying is you're studying, is that true or not? And how do we even quantify it?
Fantastic, And I think the answer I would give is they are learning a world model. It's just a mess.
I see.
And it's because, yes, they must learn the world model to predict. He's right. And then in these cases, like this map, what map of New York do they learn? We can actually see the map they learn, and it is a mess. And the way to think about it is, because they're these highly parallelized systems, our current best guess is that they're learning a patchwork of heuristics. And these
like humans, maybe.
Like humans, right? Yeah, not bad. Unfortunately, because they're working in such highly parallel, there are these very specialized heuristics. And again, it goes back to, if they get to be as bumbling around as I am, I'm not sure that's an accomplishment. I wanted to teach me something I didn't have, you know what I mean? And so I think that's the sense in which I think you put it well. I won't run on it. But I'll go back to the other thing you said, which is, if we want to go down this path, notice everything that's now needed. We need some model problems where there's actually incentives to learn the world model that we can all try and compete on. We need some evaluation metrics for whether we've learned, and we need the data. So for me in the healthcare space, if I can plug something, so for me, I wanted to do this for a while, But the biggest problem that we had was data. It's actually very easy to get data for automation. But if you want data for actually learning, did this person, what happened to them? That's hard to get data. So we have this company called Dandelion whose sole goal was to put together data sets like that. Because I think the combination of making data for augmentation and discovery, creating the right tasks, and then getting people to work on it, I think the tech stack is being built today. I have hope that enough people will get on this bandwagon that we can start to build a complementary tech stack for augmentation. But I actually think it's one of those pivotal moments in time where if we don't do this fast enough, the automation tech stack is going to get good enough that it's like people are going to be like, I don't want to do this thing down here. I can do so much up here. And then we've kind of built a future that I don't think is nearly as optimistic and bright.
Yeah, I think a lot of people are concerned about that kind of path. But there's a lot of exciting stuff and a lot of upside as well, and not least on the science side. Maybe we can end on a couple of fun speculation/prediction topics.
Great.
I want to start with math.
Great.
Let's think about how AI can improve mathematics.
Yeah.
I know you've been thinking a little bit about this as well. So maybe we can just formulate this as a prediction. So there are these Millennium Prizes. Do you think there will be a point where algorithms or some sort of AI system will solve one of these Millennium Prizes, like the Riemann hypotheses or something along those lines? If so make a case for whether you... All right, let me try to formulate it. Do you think it's going to happen ever? That seems like you probably have to answer yes to that. What's the kind of over/under for the year, and make a case for why it could happen or why it was going to be super hard.
So I'll say within 15 years, we'll not only have one of these solved, we'll have the first one I think will be solved where it'll look like human plus machine. There was a lot of whatever, but I think we'll soon quickly see ones that are completely solved by an algorithm.
Wow.
And I think that's within 15 years. And I think but I don't think that means the end of math. I'll tell you why. I think that once the problem is posed, this is not different than chess. Because once you get into a framework like Lean, it's literally just working out. Now it's combinatorially hard, but the mind doesn't have some magic combinatorial machine either. So it's literally just working out what combination of things get you to this. Now, that's why I'm very confident that one of these will be easily solved. Not easily, but it will be solved with enough people throwing stuff at it. People are trying to throw stuff at it. But it's worth noting math is two things. It is a logic activity where you try to prove something, but an aesthetic activity where we try to state that such and such is worth proving.
Sure.
So we had to come up with these millennial prizes.
So one thing is the proving of theorems.
Right, and the other is the deciding something is worth proving. What's been left unsaid in all of math is that math has a very strong aesthetic component. A very strong aesthetic component. Even when people say that,
that's a beautiful theorem,
Right, right. People talk about the beauty of the proof, but the aesthetic component is that itself is worth proving.
Yeah.
I don't see how an algorithm could ever get rid of that, because it's very different. It's something fundamentally human. But if you said to me, once the theorem is stated, which is how your thing was asked, I'm willing to bet 15 years. I wanted to say 10, but that seems so soon. So 15, there's a chance I'm not around, so it's easy to escape that possibility.
All right, so you think that's going to be can you speculate a bit further what that might look like?
Yeah, I think what it will look like is there are these wonderful lean theorem proving things. There are these innovations like we saw I think this was a Google DeepMind thing where we saw using natural language interfaces to get rid of the tediousness of putting things into lean. To say it that specifically is very hard. But semi-natural language, by natural language, I mean, if you look at a math proof, I'm calling that natural language. Yeah. Because that's not programming. Turning a math proof into lean is super tedious. You have to write every bit of stuff. But it used to be tedious to program as well. We'd have to, not just because it was punch cards, but you have to program in assembly. But then we created high-level programming languages and higher-level programming languages. I think we're going to see higher level programming languages to program into Lean, possibly with a natural language interface to convert into those. Once you have that, then I think this thing looks a lot like chess.
I see.
And then the thing will start to work its way out. But I think it's like people have known for the last quite 10 years actually. I will also note that we've already had some major theorems proven using algorithms. The 4-color theorem was actually proven using an algorithm. And so that was a very major theorem. That wasn't ML, that was brute force combinatorial search.
I see.
But I don't think we're far from that.
So do you at that point think that humans will understand the proof? Let me give you an analogy you mentioned chess. I think it's true for chess. It's certainly true for Go.
Yeah.
That the best algorithms are so good that people are still trying to figure out what the hell is going on, right? Right? And so it's not hard to imagine that this will happen in math, and we will basically still be trying to study. We know the proof is watertight because of Lean or what have you. Yeah. But the understanding of it.
So it's beautiful you asked. I'll just make 2 points. There's a famous mathematician who has asserted that math is not what is true in math, but it is the human understanding of what is true in math, which is not an unreasonable view. That is, we use math as a way to sharpen our thinking about the world, and the understanding is key. But if I take that, then I'd say we're back to the augmentation thing, which is how much energy do we put into building chess and Go? A lot. Yeah. How much do we actually put into making AlphaGo understandable to humans? Very little. Yeah, when people say like, oh, it's not comprehensible, really? So let's just compare how much effort you put. Minuscule amounts of effort. Yeah. And so I'm not convinced that those things don't have insights for Go players. Ashton Anderson is a professor at University of Toronto who I've done a little bit of work with, and John Kleinberg has done a lot of work with, and he has done some of the most interesting work on chess. And a lot of it is of the variety. What does this tell us about people? How can they tell people? And just amazing things have started to show up. That's just one team, and you already see some pretty cool stuff. And so I suspect if people actually center this activity, we'll make more progress than we have.
And that's exciting.
Yeah.
All right, so final question.
Final question. We're already out of time.
You want to continue?
What do you have to do, David? What else you got going on today?
I have kids I have to take care of. Yeah. Question about the scientific process of evaluating science, which is peer review. Will there be a top scientific journal where the peer review is done by an algorithm? So you should feel free to say, this will never happen, this may happen this year, but maybe perhaps what field do you think it could potentially happen in first, and why?
I think that if you take peer review as suggestions to an editor, and if you take it as not every referee will be an algorithm, but one of the referees will be an algorithm.
I meant like
fully done. Oh.
Explicitly by the journal.
Oh, that's so interesting.
Like, how do you think through that problem?
Yeah, great. So let me do the easier one for a minute. If it's one of the things, I think that should happen very quickly. Like in 5 years, we should have that, If it's all of it, I'm actually going to be negative on this and let me try to argue it. I don't think it's going to happen. And here's why I think it's not going to happen. If an algorithm, evaluation is much harder than generation. Evaluation requires reliability, perfect reliability. If an algorithm can be perfectly reliable at evaluating, then why the hell are we doing the generating? Like at some level, the algorithm could start generating too. If you're in a domain where perfect evaluation is possible by an algorithm, a human adds no value at the evaluative stage, then I don't see how we're going to add value at the generative stage. So it's just my off-the-cuff answer is that evaluation, which is what a referee does, is actually significantly harder than generation because it involves a ton of stuff. It's the thing where we decide what's true north. It goes back to your point about we rarely have ground truth. Evaluation is a call on ground truth, which we don't actually have. If we trust an algorithm to make that call, hell, let us just do the science. Why do we need us to be in the business of doing it? And so I'm going to be negative on that one for that reason. I think that's how I try to reason it through.
Do you have what is your view of humans in the peer review process?
You're trying to get me to say I don't like referees. I think if you look at what peer review is, that's what I was starting to say. A huge component of it should be automated. We're actually terrible at it. Peer review should check proofs, check every detail of proof.
It's very time consuming.
It's very time consuming. The meticulous part of it, which algorithms could do well, throw up errors, throw up possibilities, like that they could do pretty well, especially the more mechanized parts. That I think we should completely put into algorithms and work hard. But now there's another part of reviewing. Is this interesting? Will this be impactful? How does this relate to the existing literature? Is this interpreting the data correctly? Like if referees could be left to do that bit and take out this bit, I actually think we'll get better referees. Whereas right now, they do a weird mishmash of both and don't do it's because it's time consuming. Don't do a great job of either one. Yeah. Except my referees, they've done a great job.
All right, awesome. So we'll end there. Thanks so much, Sendhil,
Thank you, David,
for coming, and I really, really enjoyed this discussion.
Me too. Awesome.